Hi there. Welcome to the second problem in the Problem Corner playlist of the Genesis YouTube channel. This problem involves a block placed on a wedge with friction at all contacts. The problem goes like this. A small block A is kept on the inclined face of a wedge B having right triangular cross-section as shown in the figure. The wedge B is kept on the ground and its inclined face makes an angle theta is equal to 30 degrees with the horizontal. The coefficient of static friction between A and B is mu1, which is 0.7, and that between B and ground is mu2, which is 0.8. The mass of A is small m equal to 1 kg and that of B is capital M equal to 2 kg. Take G as approximately 10 meter per second square. Neglect any tendency of toppling of B. What we have to find: the contact force between A and B, the contact force between B and ground, the acceleration of A and the acceleration of B. I suggest that you pause the video and try it before moving further. It is not a very difficult question, but you need to be particularly careful with the data about friction given. If not, you can go astray and end up doing a lot of calculation. Ideally, this is the kind of question I would pose to a candidate in an interview to test his or her presence of mind and depth of understanding. At the outset, this problem seems a bit difficult as there is friction present at all contacts and it seems that the solution is going to go lengthy. However, if you keep watching to the end, you will find that the solution is very short, provided you have your ideas crystal clear. In questions involving friction, you must keep in mind that friction acts to prevent relative slipping. So, what is the best possible case to prevent relative slipping? It is the case when nothing moves. That is, it is the case of equilibrium. So the first question we ask ourselves is that, is there a possibility of nothing moving? Yes, there is. As there is friction between A and B and also between B and ground, this possibility definitely exists. So this is something we must explore at the outset. Now, before we go on to explore this, I would like to remind you of a few ideas, that of angle of repose and that of net contact force. Suppose you have a block kept on a stationary inclined surface and you keep increasing the angle of inclination. The angle of repose is that angle after which the block starts to slip. So, if we draw the FBD of the block at an angle less than the angle of repose, we have the weight mg, normal n, and the static friction Fs acting on the block. The friction is static as the block hasn't yet slipped. For equilibrium, we must have n is equal to mg cos theta, Fs is equal to mg sin theta, and for no slipping, Fs should be less than or equal to μs into n, where μs is the coefficient of static friction between the block and the incline. Substituting into the inequality, we get mg sin theta less than or equal to μs mg cos theta, which gives us theta should be less than or equal to tan inverse μs. Now this means that the equilibrium of the block will be sustained till the angle tan inverse μs. Hence, it will just start to move from this angle onwards. Therefore, theta r is equal to tan inverse μs is the angle of repose. So tan inverse of the static friction coefficient gives us the angle of repose. Any angle greater than this will cause the block to slip. Now, another very important thing to notice here is that till the block starts to slip, there are three forces which are acting on the block and the resultant is 0. Therefore, we can say that the resultant of any two of them will be opposite to the third one. Specifically, for our purpose, it follows that the resultant C of the normal force and friction should be equal and opposite to mg. This resultant C is called the net contact force applied by the incline. So recapitulating, we now know that on a stationary incline, a small block won't slip till the inclination exceeds the angle of repose, and till then the net contact force C vector is vertical and it equals mg in magnitude. Now with these two ideas in mind, we are ready for our problem. As we realize that equilibrium is a possibility for the system, we explore that first. Now remember, when you make an assumption regarding the state of a system having friction, you first find out the values of friction required to sustain your assumption. Now once you have those values, you check whether any of those values overshoots the maximum value possible for that friction. If so, then your case isn't tenable and therefore your assumption was wrong. However, if all the frictions that are required to sustain your assumption are less than the maximum possible value, then you have hit upon the situation that will actually happen. With these ideas in mind, we say, if possible, let this system be in equilibrium. If so, the incline is stationary, and therefore we must see whether this angle of inclination theta is greater than the angle of repose or not. The angle of repose will be theta r is equal to tan inverse mu1, which is tan inverse 0.7. Now don't worry about finding tan inverse 0.7 in degrees or something. We don't need to find it. Just note that for the incline, tan 30, which is 1 by root 3, is roughly 0.58. Now this value 1 by root 3, 0.58, you should remember because this is very handy in many calculations. Similar, we find that tan theta is 0.58. So 30 degree is actually tan inverse of 0.58. Now tan inverse of 0.58 is less than tan inverse of 0.7. So theta is less than theta r. Therefore this angle is less than the angle of repose, and so the block will not slip and the contact force acting on it will be vertical. This is crucial because if the contact force acting on it is vertical, its reaction on wedge B is also vertically downward, and therefore it induces no tendency to slip on the wedge B. So our assumption of equilibrium is justified as we have run into no contradictions, and our assumed frictions have not overshot their maximum values. You should note that we didn't even need to look at the value of mu2 at all, and now all our answers are oral. A. Contact force between A and B, small mg, 10 newtons. Contact force between B and ground, small m plus capital M into G, 30 newtons. Acceleration of A, 0. Acceleration of B, 0. And therefore you realize that this problem, which initially looked very difficult and very lengthy, the data was set such that you really don't have to do too much calculation here. In fact, it's negligible the amount of calculation that actually gets you the answers. So I hope that you enjoyed this problem. For many such intriguing problems, keep watching the Problem Corner playlist of the Genesis YouTube channel. Serious JEE aspirants may also want to check the Solutions to JEE 2020 Physics playlist. Till the next problem, stay safe and stay healthy you all.